We're going to be taking a look at two gas laws, the ideal gas law and Dalton's law. The ideal gas law is a law that we're going to be using a lot. The formula for it is PV equals nRT. So notice all the letters are capital except for N. We're used to seeing PV and T. We've used them before. We know what those are. The ones that are new to us are N and R. N stands for moles. You might be thinking, that seems odd, because moles starts with the letter M. Well, what actually ends up happening is because there's so many things that we use M for, for moles we call it N, as in nitrogen. It's kind of odd, but it's one of those things that we do for clarification. So N is moles. R is referred to as the it's a constant for us. It's the ideal gas law constant. So you'll notice we have three specific values listed here. Most often in ideal gas law problems, we're going to use this middle one. Notice the units that are assigned for it. You have kilopascals, liters, moles, and Kelvin. So first of all, a nice way to remember the ideal gas law is kind of thinking of it as PivNert, so kind of adding an I and an E. So I'm going to put this in quotes because the I really isn't there and the E isn't there. But PivNert, I'm going to highlight those fake letters in pink. PivNert is a way to help you remember it, but it's PV equals nRT. So R is a constant. R is a constant that you're going to need to know. For us, to simplify it, we're always going to be looking at our units of pressure. All the other units are the same. K stands for Kelvin, L stands for liters. There's actually probably there's probably a couple dozen of these variables, these R's that you can use. We're just going to limit it to the three. Most often you're going to use the center one that I have circled. However, you could potentially see either of the others. A nice way to help you remember your units here is by saying kind of kapow, like kapow, like in the cartoons, but with an L at the end. Kapow, or a molk. So kapow molk. Or sometimes people say kamol. Whatever works for you. You don't really walk around talking about ideal gas law problems, so you're not really announcing it to anyone, but you can use that to help you remember. So this is kind of where the kinetic molecular theory, or KMT, comes into play too, because we really need our gases to be ideal here. And although we don't really have something as called an ideal gas, the theory still helps us to explain the properties of gases, so we're still going to continue to use it. So here we have our first problem. We're looking inside a nitrogen-filled tennis ball. So these problems are going to look a little bit different. For our first four gas laws, we always had a change that occurred. So, we changed altitude, or we changed the environment, we changed the temperature, we changed something, and we wanted to see what the effect was on the other variable. For these, we're not going to have that change. We just have an environment, and we're trying to figure out exactly what's happening in that environment. So in this case, we have a 34 degrees Celsius. The pressure inside a tennis ball has a volume of 0.148 liters and a pressure of 212 kilopascals. How many moles of nitrogen gas are filled inside the tennis ball? So in this problem, if you think of PV equals nRT, we have the temperature, we have the volume, and we have the pressure. R we can get because we know it's a constant, so we're going to be solving for N. So our R value that we're going to use, because our pressure is in kilopascals, we're going to use an R value of 8.315 kapal molk. in order to help us describe it. So we're going to fill in everything else. Our pressure is 212 kilopascals. Our volume is 0.148 liters, and our temperature is 34 degrees Celsius. N is going to be what we solve for. N is quite often the most common variable solved for in these types of equations. However, you could solve for anything else, even R sometimes. So just like before, our temperature has to be in Kelvin, so we're going to add 273.15 to this. Because we only have a significant digit in the ones place, we're going to round it to there, and we're going to have so we're going to get 307 Kelvin for our temperature. We now have all our variables. This equation I think is a little bit easier to rearrange. We're going to have N is equal to PV over RT. So we can now plug in our variables. So we have P 212 kilopascals times volume of 0.148 all over our constant 8.315 times 307 Kelvin. So notice with our constant, the units are all canceling. Kilopascals cancels, liters cancels, Kelvin cancels. We'll be left with mole. Now, because we're dividing by a fraction, your unit is going to end up being mole, which makes sense. So now we can calculate this. Just like before, sig figs, we're taking a look at the quantities that we have. We're going to be limited by actually most of our values. We have 3 sig figs in all of them, so we're going to have 3 sig figs in our answer. So we end up with 0.0123 moles inside our tennis ball, which makes sense if you consider the size of a tennis ball. So this was a very small example. In the next one, we have a larger example. We are in a deep underground cavern, and we know the volume, and the pressure, and the temperature. We want to know how many kilograms of methane is inside the cavern. Now, we don't have a way to directly get kilograms. However, we can calculate moles, and we know how to convert from moles to grams, which we can then convert to kilograms. So yes, we're still going to be using mole conversions. So we have our variables lined up. We're again solving for N. Notice how all of our units are matching. We're already in Kelvin, so we don't have to convert it. So now our units cancel. We have kilopascals and kilopascals, liters, and Kelvin. And again, we're going to be solving for moles. Now, the last problem, we had an extremely small space we had inside a tennis ball. Now we have an extremely large space of cavern. So this number will tell us the number of moles of methane, which is CH4. We won't be done once we calculate this, but this is what we need in order to get to the next step. Let's think for a moment, though. We do know with mole conversions we have the 22.4. However, that only works if we're at STP. So for this problem, we are not at STP. Our temperature doesn't match and our pressure doesn't match. So we can't do that method. There is an alternative way of doing this using the combined gas law, getting it to STP, and then doing a mole conversion. However, it's more work and more steps. So the ideal gas law is a way to kind of work around that. So we end up with 1.28 times 10 to the 6 moles of methane. So we do have to do a quick mole conversion to go from moles of methane to grams of methane. So to go to grams, this is where we use molar mass on the periodic table. We would add up 1 carbon and 4 hydrogens, which would be 16.05. So we're going to take the number we got and multiply it. Now, when you calculated this first number, you should have had all of the numbers in your calculator. You shouldn't be rounding midway through the problem. However, since it's, we finished the equation and then we're multiplying, you technically should keep the number in your calculator, multiply it by 16.05. However, if you take the rounded number and multiply it, that's fine too. So you're going to end up with 206. Really big number of grams here. So that's 20 million grams of methane here, which we should probably write in scientific notation as 2.06 times 10 to the 2.06 times 10 to the 7th grams of methane. So just a reminder about ideal gases versus real gases. Ideal gases assume we have no volume and that there's no attractive forces between particles. In real life, gases have these things, even if they're small. Most real gases differ most from an ideal gas at low temperatures and high pressures. We forgot a step on the last problem. The problem did ask for kilograms, and we left it in grams. So we do need to do one more unit conversion. There's 1,000 grams in a kilogram. So we're going to take our number, divide it by 1,000, and we're going to end up with 20,600 kilograms, or 2.06 times 10 to the 4th kilograms of methane. Either would be acceptable as your final answer. Next up, we have Dalton's law of partial pressure. The total pressure exerted by a mixture of gases is the sum of each individual gas. So for these problems, if you were able to separate the gases out, each individual gas would behave independently of the others. So we have the total pressure is equal to all of the individual. So looking at this example, let's say we had oxygen and nitrogen present in a flask. The way we describe it, we say P of the specific gas. So P of O2 plus P of N2 is going to be equal to the total pressure, P total. So for this problem, we have the total pressure of nitrogen is 250. Total pressure of oxygen is 300. So the pressure of nitrogen is 250. The pressure of oxygen is 300. So the total pressure is adding those two together is 550 millimeters of mercury. Looking at that problem, you literally just add them together. Now, because this is written in scientific notation to help us with sig figs, the 3 and the first 0 are significant, so when we add them together, we get both 5s to be significant. Most often with these types of problems, we're going to have, in the next problem, when we collect gases, usually we collect it over water because it helps us to measure the amount of gas that we're getting. So if we collected CO2 gas over water at 25 degrees Celsius, and atmospheric pressure, the partial pressure of water vapor at 25 degrees Celsius is 0.54 atmospheres. What is the partial pressure of the dry gas? So this is referred to as drying your gas. Anytime you're collecting over water, water is going to contribute to the pressure. Now, depending upon exactly what temperature it is and the atmospheric conditions, is going to determine the pressure of your actual gas. When most of the time, P total is going to be the same as P atmosphere. So if your pressure of the atmosphere, your barometric pressure, is usually your P total. So for us, it's going to be 1 atmosphere. The partial pressure of the water vapor, so P of H2O plus the pressure of carbon dioxide. So we know the pressure of carbon dioxide. They told us it was, we know the pressure of the water is 0.54 atmospheres. And we know the total is 1.00 atmospheres. So we have to solve for CO2. All you have to do is subtract to solve for X. So your X, which is your pressure of carbon dioxide, is going to be equal to 0.46 atmospheres. Things to keep in mind with Dalton's law, sig figs can be a bit tricky here. Remember, you are using addition and subtraction, which have different significant figure rules where you align it by the decimal place. That's kind of the trickiest part of these problems. Otherwise, these problems are pretty straightforward. So the last thing for today is talking about mole fractions, which is the ratio of the moles of a given component in a mixture to the total number of moles in the mixture. So at a constant volume and temperature, mole ratios and pressure ratios are going to be the same. So in order to calculate the mole fraction, which is kind of this scripty x, so in this case we have the partial pressure of oxygen. So just like with the partial pressure of gases, we're going to say what we're looking at. It's going to be equal to the partial pressure of oxygen divided by the pressure of the total, P total, or P of the atmosphere, or barometric pressure, to determine the fraction. So we're going to take 156 torr divided by 743 torr. Notice also we're not multiplying by 100, we're just dividing. It should be a fraction, it should be less than 1. So we're going to take 156 divided by 743, and just like before, sig figs would matter here. You would, if you're dividing, you would look at the quantity. So we're going to have 3 sig figs in our answer, so we're going to have 0.210. Also keep in mind our mole fraction doesn't have a unit. We just divided out our units of pressure, so we won't have a unit associated with our mole fraction. So I just want to talk quickly about how you measure these things. The first one here is atmospheric pressure. We measure this using a barometer. You may have heard of a barometer. It used to be filled with mercury, and that's how we got the unit millimeter of mercury. In modern barometers, they usually use some sort of alcohol. The key is you want something of high density, so you don't need to have it be extremely large. A water barometer would work. It would just be approximately 3 stories high, which is a little bit impractical. But anyway, what ends up happening, you have a container that's open to the air, and then atmospheric pressure is pushing on this, and that's going to change the height of the mercury in the barometer. So at the very top, you have an empty space. If you didn't already know this, as weather moves through, the pressure changes slightly depending upon what type of pressure system. If you ever had someone, maybe they get a headache every time there's a big storm, or their elbow hurts or something, that's due to the pressure change from the weather. Sometimes as your body gets older, you can kind of get a spot that the air doesn't escape very well, and can cause pain when a big weather system moves through. So that's a barometer. The other thing that we need to look at is a manometer, which you spell like manometer. The big difference here, atmospheric pressure, so pressure of a room, for example, would be measured with a barometer. If you had a sample of a gas, you would be using a manometer. In modern days, we usually have gas pressure sensors that we use in order to determine gas pressure. But what you're doing is you're comparing the atmospheric pressure to your gas sample, and you're either adding or subtracting the height difference. So taking a look at the first example here, we have a flask with a gas inside of it. This one, the gas inside has a higher pressure. I know this because the gas is pushing down harder than the atmosphere. You can think of this as kind of like a tug of war. So either the flask or the atmospheric pressure is going to be higher. The one that is higher is going to be able to push down lower. So in this example, we have a greater pressure. So our atmospheric pressure for these examples is 760. We have a 200 millimeter of mercury difference. So we're going to take 760 and add the 200 millimeter difference to get a total pressure of our gas sample of 960 millimeters of mercury. Now, for calculating pressure using a manometer, I'm not going to be worried about sig figs here. So for the other one, 760, we have the flask. The mercury comes higher, so we were going to subtract. So you end up with 410 millimeters of mercury. So it just depends on the situation. I always think of the flask versus the atmospheric pressure.